All right, today we're going to jump into something that's like at the very heart of mathematics, functions. I know, they can sound a little abstract, but trust me, by the end of this, you'll see they're actually just really simple, super powerful tools. You ready? Let's get into it.
So, what if I told you there's a rule? A rule that can map anything to anything else, but with one super important catch. Think of it like a machine. You pop something in one end, and something else comes out the other. A function is basically that machine, but it has this one very strict, very crucial rule that makes it totally unique.
Okay, so here's the game plan for today. We're going to start with, what is a function? Then we'll take a look under the hood at its anatomy. After that, we'll talk about something called image and pre-image, which is all about tracing its path. And then, the really cool part, we'll get into how to classify all the different types, all leading up to this one special kind of perfect function. All right, first up, what is a function? And really, it's more than just some equation you see in a textbook. Forget all the complex formulas for a minute. At its core, it's just a rule, a simple, reliable instruction.
And here it is. This is the big one, the golden rule. A function is a rule that assigns each input from a set, let's call it set A, to exactly one unique output in another set, set B. That's the key phrase right there. Exactly one. Not two, not zero, always, always one.
So let's go back to our machine. Every single input has to have an output. And here's the kicker. An input absolutely cannot have multiple outputs. So if you put the number 2 into your machine and it spits out a 4, it will always spit out a 4 for the number 2. It's not going to suddenly give you a 9 one day. Nope. One thing in, one specific thing out. That's the deal. That's the essence of a function.
Okay, so to really get how this machine works, we need to look at its three main components. Let's pop the hood and talk about the domain, the codomain, and the range.
First up, the domain. This is basically the pile of all the raw materials that are allowed to go into our function machine. It's the complete set of all possible inputs, set A, everything you can start with. Then we've got the codomain. Now this is the set of all possible outputs the function could create. Think of it like the entire warehouse of potential products our machine could make. It's every single value our function might land on, even if, it doesn't end up using them all. And that's where the range comes in. The range is the set of all the actual outputs the function produces. So it's not the whole warehouse of possibilities. It's just the products that actually come out of the machine and get shipped. The real deal. So let's tie this all together. The domain is our input set, set A. The codomain is our potential output set, set B. And the range? Well, that's the set of all the actual f of x values we get. And here's the most important relationship to remember. The range is always a subset of the codomain. It can be the same size, sure, but it can never be bigger. You can't get an output that wasn't on the list of possibilities to begin with. Okay, let's look at a quick example to make this super clear. Let's say our function is f of x equals 2x plus 3. And for our domain, our inputs, we're only allowed to use the numbers 1, 2, 3, 4. Well, what happens? You plug in 1, you get 5. You plug in 2, you get 7, and so on. So our range, the actual outputs, is 5, 7, 9, 11. See? Now, maybe the codomain had all the integers in it, including the number 6, but 6 is not in our range, right? Because nothing in our specific domain can produce it with this function.
All right, now that we have the main parts down, let's talk about tracing the connections between them. We can follow the path forward from input to output, but we can also try to work our way backward.
So when we go forward, the output you get for a given input is called its image. Easy enough, what comes out of the machine. And for every input in the domain, an image is guaranteed to exist. But what if we go backwards? The input that led to a given output is called the pre-image, what went into the machine. And here's the twist. A pre-image might not exist for every single element in the codomain.
Let's stick with our f of x equals 2x plus 3 example. The image of 2 is 7. That's looking forward. The pre-image of 7 is 2. That's looking backward. But what's the pre-image of 6? It doesn't exist, right? There's no number in our domain of 1, 2, 3, 4 that you can plug into that function to get 6. And this distinction, this idea of whether a pre-image exists or not, is going to be absolutely critical for what we talk about next.
So, it turns out that this whole idea about pre-images is how we can start classifying functions. We can sort them into different types,
like organizing all of our different machines based on their specific behavior.
Yeah, it actually boils down to asking two really simple questions about the preimages of a function. Question 1, does a preimage exist for every single element in the codomain? And question 2, when a preimage does exist, is it unique?
And check this out. This grid lays it all out perfectly. The answers to those two questions, does it exist for all and is it unique, gives us these 4 distinct categories of functions. This is basically our whole classification system in one chart. Let's break down what each of these boxes means.
Okay, let's start with that uniqueness question. On one side, we have one-to-one functions, which are also called injective. This means every single output comes from exactly one unique input, no sharing allowed. On the other side, you have many-to-one functions. This is where at least one output comes from 2 or more different inputs. A perfect example is f of x equals x squared. Think about it. Both 2 and -2 give you the exact same output, 4. That's a classic many-to-one situation.
All right, now for the existence question. If a function is onto, also called surjective, it means every possible output in the codomain actually gets used. The range is equal to the codomain. Every target is hit. But in an into function, there's at least one poor, lonely value in the codomain that never gets mapped to. It's left unused. In this case, the range is a proper subset of the codomain.
So, you might be wondering, what happens when you get the best of both worlds? What if a function meets the strictest criteria? What if it's both one-to-one and onto? Well, then you get something really special.
We call this a bijective function, and it's not really a totally new type. It's just a name for a function that is both one-to-one and onto, a powerful combination.
So, just to be super clear, for a function to earn the title bijective, it has to check 2 boxes. First, it's got to be one-to-one or injective. Every preimage that exists has to be unique. And second, it has to be onto or surjective. That means a preimage has to exist for every single element in the codomain.
What you end up with is, well, it's a perfect one-to-one correspondence. Every single input maps to a totally unique output, and every single possible output is mapped to by exactly one input. There are no leftovers, and there's no sharing. It's this beautiful, perfect, and totally reversible mapping between 2 sets.
And that's the idea I want to leave you with. A bijective function creates this kind of perfect one-to-one world. So my question to you is, where might a perfect mapping like that be absolutely essential? Think about fields like cryptography, or coding, or data management. Where would you need that kind of perfect, unambiguous connection?